So here in our Talk the Thought process, we're going to talk through how we come up with some electron configurations and then relate them to the trends we see in the properties and reactivities of elements in the periodic table. So here's a lovely picture of the periodic table, and this is a version provided by the textbook I use in my class, Chemistry, an Atoms-Focused Approach. And we see here the color coding that the S block here is in green, and that means that the outermost electrons are in S orbitals. And here the P block is in blue, and as we know, it's 6 atoms wide because there are always 3 P orbitals in any shell. And there are 2 electrons per orbital, so therefore there are 6 atoms that fill up the P subshell. We also have the D block here, which is 10 atoms wide. So we can just march across the periodic table and see the electron configurations by putting in 1 electron at a time as we go from left to right, and then we remember our rules for putting in the electrons. So let's write the electron configuration for calcium. Okay, so for calcium, we have to find its place in the periodic table, and we can go right back here, and we can see where it is. So the electron configuration looks like it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So let's write that down here. We said it was 1s2, 2s2, 2p6, and then to the third shell, 3s2, 3p6, and then to the fourth shell, sorry, that's a 6, 4s2. Right, so we know the third shell has also d electrons, but we see from how the periodic table is arranged that we fill the 4s orbitals before we fill the 3d, before we get into that d block. So that's our electron configuration of calcium. And so an abbreviated way to write that is to look at the full shell before calcium in the periodic table, which here would be argon, and then just put in what comes beyond that full shell of argon. So it would be argon 4s2. So that would be our other way of writing the electron configuration for calcium. That would be also, this is the same thing as argon 4s2. And that's because all of this represents the full shell that is argon. It's argon there. All right, so then when we go to calcium 2, right, this calcium is neutral. When we go to calcium 2, we have to take away 2 electrons. And we see that if we take away those 2 electrons in the 4s2, we end up with the full argon shell. I always say a full shell is a happy shell, so this one is a happy one. And so this is why in group 2, which we are here, the elements lose 2 electrons to form +2 cations, because when they do that, they become a full shell, just like in any of these would do. Group 2, right? Any of them, we take away those 2 electrons and they'll be like the noble gas that precedes it in there. Okay, so the next one we want to do is bromine. And so bromine is further away from calcium. So we can keep going on from calcium all the way over here. So we're going to fill up all of this D shell and then get over here to bromine. Okay, so let's start with argon, the full shell in argon, and then we'll add whatever comes after that all the way to calcium. So it'll be argon 4s2, 3d10, and then 4p5. So let's write that one down now. So that would be the full shell of argon, and then 4s2, 3d10, 4p5. Right? Let's look back to make sure. Argon 4s2, 3d10, 4p5. right? And so we see that bromine here is very close to krypton. And if we just added one electron, it would get to the full shell of krypton and be a real happy full shell. And so that's why we form bromine minus, which is bromide, right? If we add bromide, then we'll have argon, 4s2, 3d10, 4p6, which is a full shell of krypton, otherwise known as krypton. Okay, and so that again shows us why in the 7th row, or sometimes called in the 17th row, over here we have the halogens, and they tend to form the halides, which are negatively charged ions, because that helps them to look exactly like the full shell. Okay, so there we are. Filled shell is a happy shell. And that is why we can see these patterns in reactivity. For example, that the elements in group 1 give up an electron to form +1 cations. Group 2 give up an electron, 2 electrons to form +2 cations. Group 7 adds an electron to form -1 ions. Group 6 will add 2 electrons to form -2 ions. Also, they can get close to or the same configuration as the full shell that is nearest to it in the periodic table. So now if we look within these columns in the periodic table, what do we expect to happen? Well, which is bigger, magnesium or calcium? So if we look at the periodic table, we'll see that calcium is below magnesium, right? And as we're adding shells and we go down, the atoms get bigger, right? Because we're adding full shells as we go down here. So calcium is bigger and magnesium is smaller. And so which one's going to be better at giving up its 2 electrons? Well, the one that's smaller has those 2 electrons bound more close to the nucleus than the one that's larger, right? And so the one that's larger is going to be better at giving up those 2 electrons. And that's the type of trend that we would see. And it makes sense when we think about the shells. Which is bigger? The one farther down in the periodic table. Which is better? The one farther down in the periodic table. Which is more reactive? The one farther down the periodic table. And that's because these are giving up electrons, and those electrons they're giving up will be farther from the nucleus as you go down the periodic table. Now, what do you expect when you look at the elements that tend to gain electrons? Oxygen is sulfur. So we can again look at the periodic table. Let me go back. Oxygen and sulfur over here in group 6 or 16. And so both of them would like to gain electrons in order to form the O2 minus ion or the S2 minus ion, right? Because that would make them be more similar to neon and argon. Well, which one is going to be better at gaining electrons? Okay, so here with oxygen, the electrons to be gained are going to be closer to the nucleus than the electrons to be gained by sulfur will, right? Because the sulfur is bigger. So we kind of see the opposite trend as we did over there, because here we're gaining electrons rather than losing electrons. And it's going to be easier to gain electrons when those electrons go into kind of slots that are closer to the nucleus. So again, we'll see that same kind of trend in reactivity, which is better at gaining electrons, the one that's smaller in this case, right? The oxygen will be better at gaining electrons. So that's a little bit of talk the thought process, thinking through the electron configurations, how we write them in the longhand, how we write the condensed version, and then how we see by especially writing the condensed version that we have patterns in reactivity and patterns in the properties of the elements.